Okay, let's start. Do you have any questions? Okay. So last time we were discussing 3.4, right? System with complex eigenvalues and eigenvector. So system with complex eigenpairs, right? And so the idea is, right, that if you have y prime equals to ay, right, and you got lambda, right? So if you assume the 2 by 2 case, then you got lambda equals to a plus minus bi as the eigenvalues, right? And you got correspondingly v, right? A vector v1, right, and vector v2, which is a conjugate of vector v1 as eigenvectors. Okay. And so to find the solution, you start out with, right, the solution yt, which, right, is going to be e to the a. Let's say you pick one, right? Doesn't matter. A plus bit, right, times v1, and then you split this, right, into the real part, right, a real part, and then the imaginary part. So let's do that, right? Let's say it's y1 t plus I y2t. Okay. So if you convert this into this, then your solution will be c1y1 plus c2y2, right, as real value solution. Now, in terms of classification, right, classification and sketching, right, and sketching solutions, right? So we still have, right, the origin 0, 0 as the only equilibrium. And so we have three cases, right? This value right here, right, the value of A will decide the cases for us. Case 1, when A is positive, then the origin is a spiral source. Okay. And of course, the solution goes out, right? We will sketch, we won't give the sketch. You saw that before. If A equal to 0, 0, 0, right, is a center. And if A is negative, then 0, 0 is a spiral sink, right? In all of these cases, right, we determined the orientation of rotation. So in other words, clockwise or counterclockwise, right, by a test, right, on the vector field. There's this additional question of the tilt, right, of the tilt of the ellipse or of the spiral, which I think I don't have a good intuition on, and I don't think it's like, you know, a quick presentation, so we will skip that, right? But in reality, the tilt, right, is also an important component. Oh, sorry, not stilt, right? Tilt, the tilt, not the stilt, the tilt of an important component that we skip, right? Okay. So in other words, when you sketch these things on the homework on the exam, you don't have to really take care of the tilt. but right, be mindful that the graph looks ugly without, okay, or it looks not complete, that doesn't look right, okay. So that's why the machine will help you get a better picture. But if you just want to get a rough idea, this is okay. All right, so that's what we had for complex eigenvalues. Any question before we continue? All right. So 3.5 is what we will discuss today. This is a case of repeated eigenvalues. But more importantly, okay, this is for, what do I want to say here? Not for set of eigenvectors. Okay. So let's see if there's an example that we can use. So let's consider an example. So y prime, let's say, is going to be -2, 1, 0, -2y. Okay. Now this one can be done, right? This is a partially decoupled system. Right here. So you can just solve it explicitly by solving the second coordinate first, then plug in and solve for the first coordinate. Okay, so it can be solved, right? Using, right, the discussion, the substitution technique we discussed. Okay, so that's fine. But what we want to do here is we want to look at this system from the eigenvalue, eigenvector point of view. All right. Oh, sure. Actually, some of your quiz also was that. But so what was it, right? What you look at is, right, y1, y2 prime is, right, literally -2y1 plus y2. And then here is minus y2. So what you do, right, is you notice that the second one is only involves y2. So you solve. And then after you solve for that, you plug into the first equation, which only now becomes an equation of y1, and then you solve it. That's a technique of partially decoupled system. Okay. Yeah. So, but right, I mean, that's very special. And by the way, right, I mean, repeated eigenvalue system doesn't have to be the same as partially decoupled system either. We just pick an example like this to demonstrate the idea, okay, of the eigenpair. But you know, so the more important one is the eigenpair point of view. All right. So first, right, to look for eigen, so to repeat, A is -2, 1, 0, -2. We need to find eigenvalues, right? So determinant of A minus lambda I, right, will be, well, actually, we don't need that. I'm working too hard, right? Blah, blah, blah. pay attention. This is a upper triangular matrix, right? So the eigenvalues is right up there. So lambda equals to -2. Okay. If you want to emphasize, you can do that. So that's a repeated eigenvalues case. Okay. So if you look at, right, if you plug in lambda equals to -2, we got 0, 1, 0, 0, right? So in this case, you only have one eigenvector. Is that okay? So that exactly, right, is what we mean by not full set of eigenvectors. Because here, if you have a 2 by 2, full set of eigenvectors means you need to have two eigenvectors. However you obtain that. Right here, you only have one eigenvector. So that's what I mean, okay, by not full set of eigenvector. I repeat, A only has one eigenvector. Okay, so this is why I call a not full set. All right, do appreciate this. This is not like because I overlook something, right? Like on the quiz, you guys are supposed to find 3, right? That was the last quiz of last week, right? Not the most recent one. There was a repeated eigenvalues, right? But it had 2 eigenvectors. Some of you missed, right, the second one, but that's just you overlooking things. Here, I'm not overlooking anything. All right, there's only one eigenvector. Okay. So truly, there's only one eigenvector. So of course, right, I think we mentioned this before, this causes a problem for us to construct a solution. Because let's say, right, we do know something like this is true. Okay. Now, but right, because it's a 2 by 2, you need 2 degrees of freedom. The question is, where does the second guy come from? Okay, how do you go about finding the second guy? Now, for this, right, let's take a detour, all right, to the second order equation. And for that, let me just quote an example. Let's say y double prime minus 2y prime plus y is equal to 0. Okay. Now, how did we handle, right, these equations? We find the characteristics equation, right? Note that actually, in terms of notation, is very much in the same flavor as, I didn't write down, right, as the determinant equation. These are very much connected, all right? And also, of course, we can transform this to a system, right? So anyway, here you got lambda equals to 1, right, as a repeated root. If you remember, how do we construct solutions here, right? Y1, right? So y1 of t is e to the t, right? But then here, the second solution is easy. It's t e to a t. Okay. So the general solution is c1 e to a t plus c2 t e to t. Okay. So there's this idea, right, which you have seen. I mentioned it, mentioning it from like even first order equation. When you have coincidence of roots, right, multiplying by t will get you out of it. Okay. So this kind of consideration, and there was an example in the first order equation too, kind of tells us that maybe we just take this guy multiplied by t and we're done. All right. So unfortunately, right, that's the right idea, but but at least leading to a wrong solution. We need to modify it. But roughly speaking, right, to produce a second solution here, we will do the multiply by t trick. All right, as exemplified here. Okay. So in other words, you search for the second solution somehow. And let's say naively, okay, as this. Motivated, sorry, minus 2t. Motivated from consideration like this. All right. Any question here? I'll show you that this doesn't work, okay? I'll show you that this doesn't work. It needs a more, again, careful analysis. But basically, the emphasis here is that there's the multiplication by t, okay? Multiplication by t as the theme, like this, okay? Any question? So, all right. So first of all, right, do notice that when I multiply by t, I do produce a independent solution, okay? E to a t and t e to a t are two different functions, okay? So if this is y1 and if this is y2, it's fine, all right? It's fine, meaning like they're independent. But unfortunately, y2 like this, okay? Um, what do I want to say here? But this won't work, okay? What do I want to say here? However, this won't produce the right solution. In other words, if I were to construct my solution like this won't be right. This is not right. Okay. Actually, I'll take it back. I take it back. Actually, something I said before was quite wrong. Does anyone see what's the trouble with constructing this solution? Or what's the trouble of calling this the second solution? Sorry, okay, I said something wrong before. But observe this. Do you see any trouble with calling this a solution? Yeah, so exactly. Yeah, I said independent. I was completely wrong, okay? It's not independent, sorry. So this won't produce a second independent solution, okay? Now, for example, look at this. It's very obvious that no matter what you do here, the second coordinate will always be 0, right? But I guess intuitively, it cannot be that the second coordinate of this solution is always 0, because, right, from the partial solution, right, from the decoupled system, you see that it cannot be 0. Okay, so exactly in the vector notation, right, in the vector notation, this will not be it will not produce independent solution, because you, roughly speaking, right, you are multiplying with the same vector, okay, just with different scalar. With the second order ODE, this and this are actually different. That's fine, okay? In terms of scalar, this and this are two different solutions. But in terms of vector, unfortunately, you see, lining this and this up, will basically give you the same straight line solution, if you will, right? Basically, it lines up on the same line. Actually, the line here is 1, 0. Okay? So multiply by t here naively does not do anything. Any question here? Okay, so we still, right, I guess back to square one. In other words, you have the first solution like this, but we still could not find the second solution yet. But so for that reason, right, we will approach this, we approach the problem abstractly like this. Okay, that suppose that y of t, okay, is c1 v1 e to lambda t plus c2 v2 t e to lambda t. Okay, suppose that we have a structure of the solution like this. Now, again, where does this come from? This comes from exactly, the motivation that you multiply with the t, you obtain the second solution. But the difference, right, is you hope that v1 and v2 will be different somehow in the abstract formulation. It's the same lambda, okay? It's the same lambda because it's repeated eigenvalues. You hope that somehow this will be different, okay? But what we'll do is we will plug this abstract structure into the equation. We plug this into y prime equals to ay and see what v1, v2 must be. Okay? So in other words, playing with the pure guess multiplied by t won't work. So to discover the right structure, we start with the abstract guess. And then we plug that into the equation and see what v1, v2 must be in terms of their roles in relation with a and lambda. Okay? So proceed, right? First we differentiate. Differentiate will give us c1 lambda v1 e to lambda t. C2, right, has t in two places. So it must be C2, right, V2, and let's say you got lambda e to lambda, sorry. If you differentiate t, then you got e to lambda t. If you differentiate e to lambda t, you got lambda t e to lambda t. Okay. And this is supposed to be equal to a times y, right? Which is c a v1 e to lambda t plus, sorry, c1, c2 a v2 t e to lambda t. Is this okay? This is the plug-in that I talked about, right? I plug this structure into the equation, and then I will compare to see what makes them equal. All right. Now, what makes them equal? So to be equal, right, there are two terms here. The first term is something e to lambda t. The second term is something t e to lambda t, right? So whatever that is, that multiplied by e to lambda t on both sides must be equal. Then, and whatever it is that multiply t e to lambda t on both sides must be equal. So this is like comparing coefficients, okay? Because right, the idea is they must be true for all values of t, right? They must be, this is a function of t. They must be true for all values of t. That's why these guys become, right, like the highlight, that the coefficients of that assigned to them must be equal. All right, so what does that mean then? Right, the one that multiplied by e to lambda t here actually have two parts, right? The v2 and lambda v1. And here you have AV1. So in fact, you discover that AV1 must be equal to lambda V1 plus V2. Okay, again, V2, lambda V1, AV1. These are the stuff that associate with e to lambda t. What about t to lambda t? You got AV2 here, you got lambda V2. So actually, that is the familiar stuff. Okay, so let's rewrite this one more time. What this is will be AV2 is lambda V2, A minus lambda I V1 is equal to V2. Okay. So what does this mean? The first equation is our familiar definition. This means that V2 is the eigenvector corresponding with the eigenvalue lambda. But do remember, right? So in that sense, the V2 is our 1, 0 right here. The V2 is our 1, 0 right here. And so actually this structure that we are making an abstract structure of is this guy right here. Is that V1 is not the same, right? This guy is not right. Our equation says V1 must be this guy. What does this mean, right? This actually is referred to as V1 is a pseudo eigenvector for lambda. Okay, that's the terminology for it. It's a pseudo eigenvector. So it's not an eigenvector, right? It's not an eigenvector. A pseudo eigenvector is a structure where basically suppose that corresponding to lambda, okay? Lambda has multiplicity 2, right? Has algebraic multiplicity 2. But we only have one eigenvector. So to find another one corresponding to it in whatever meaning it is, you plug it into the right-hand side, you put into the right-hand side, repeat the structure, right? So obviously, right, if you want one more time, the structure is like this: A minus lambda I V2 is equal to 0. Okay, we're familiar with this, right? So we solve for V2 by the homogeneous system. That's exactly this one, right? Even though we call it V1 here because we solve for it first. This is V2, right? In our current discussion. And then after you find V2, you plug it to you put it as a right-hand side. So this is a non-homogeneous system, like that. Okay, and you solve for V1. The miraculous thing, okay, pay attention, is somehow this system is always consistent. It's miraculous because, again, right, if you recall your linear algebra day, a non-homogeneous system does not have to have a solution, especially when this is not invertible. So it's only consistent if somehow, right, V2 is in the column space of this. But it is in the case of repeated eigenvalues with only one eigenvector, with non-full set eigenvector. This is always consistent. So you will always be able to find pseudo eigenvector. all right? And after you solve for it, then you can plug it back to this structure and get your solution to your OD, all right? So, and this is the right solution exactly because of our analysis right here, okay? Because everything got matched up if we solve this system. Okay, so to recap, okay, suppose if A is 2 by 2, right, with repeated eigenvalue lambda, okay, and only one eigenvector, V2, okay, then we solve, right, for V2 by A minus lambda I, V2 equals to 0. And then we solve for the pseudo eigenvector for A pseudo eigenvector. V1, okay, by A minus lambda I, V1 equals to V2. So this is step 1. Step 2. Step 3, our solution will be C1 e V1 e to lambda t plus C2 V2 t e to lambda t. All right. Pay attention. The position is very strict, okay? The eigenvector is associated with t e to lambda t. The pseudo eigenvector is this. If you swap their places, you won't get the right solution, okay? Because, right, again, things don't match up the way they're supposed to. Any question before we apply this to our example? So for our example, right, we got y prime equals to minus 2, 1, 0, minus 2, y. We already found that lambda equals to minus 2 as a repeated root. We already found V2, right? Now we switch the notation to be 1, 0. Okay. So then the step now tells us that we find V1, right, by looking at A minus lambda I, right? V1 equals to V2. If you plug in, you get 0, 1, 0, 0, right, times V1 is equal to V2, which is 1, 0. So what is V1 here? Yeah, V1 equal to 0, 1 work. But in fact, any other choice? Yeah, V1 can be anything. Okay. Is that surprising? Is that surprising? Well, it's not surprising, okay? How do I, what can I, what do I want to say here? So it's not, we'll go back to this, but anything here would work, okay? So, but pick one. So let's say this one, okay? Let's say this one. Then your solution, y of t, for example, will be C1, okay? V1, right? Let's just pick 0, 1, e to the minus 2t, and then C2, right? 1, 0, t e to minus 2t. That's the answer, okay? That's one possible answer. Any question here before we discuss this guy a little bit more? Oh, am I wrong? No, it cannot be anything, right? No, Ron, I apologize. You're right. It's not anything. Let me, thank you. No, it's not anything. I'm sorry. No. Let me do this. Sorry. No, you're right. All the choices for V1. Okay. Yeah. Daniel, I apologize, guys. We will be more systematic. Okay. But you're right. Something like that. I was too hasty. We'll write down more carefully. Lauren, why I included this? Yeah. So okay, Lauren, right? What's the story? Okay. The story we told so far, okay, in the classes like this. Where is it? We have a system like this. Okay. If you investigate the system, you see that it has repeated eigenvalue, but only one eigenvector. So if you were to write down the solution, you only have one solution. You don't have a second solution yet. Okay. So remember, right, in this system, 2 by 2, 3 by 3, etc., you need exactly n solutions. So you know that you need the second guy somehow. But where does the second one come from? A failed attempt is to do this. Basically, to take the first one and just multiply a t with it. It's not a, coming from nowhere. It comes from a general intuition that if you have repeated solution, you just multiply, the repeated one with a t, and you get out of the repetition. The issue here is if you multiply by t, you won't produce an independent solution. Okay, so this is a failed attempt. But that doesn't mean that the structure doesn't work. We just have to be more careful with it. So the generic structure that we propose is this. Okay, where we hope that V1 and V2 are different. We hope that V1 and V2 are different. So that, right, if V1 and V2 are different, then these are two genuine solutions. These are two genuine solutions. Okay. So in other words, V1, V2, in our example, right, like 1, 0 and 0, 1 are our V1, V2. Correct. V1 is the pseudo eigenvector. Correct. And exactly, so when we plug this structure in, right, for Lauren, you ask for IT, right? YT is because, you should ask a question here. Why there's a T here? Why can't there be a T? Why can't we propose this? Right? Like, I'm not sure if Lauren has that kind of, idea in mind, but yeah, I mean, in general, why can't we just do this? Why complicate our life and put a T there? I'll put a T in, okay? That's a correct one, but why do I need a T there? Why not this? Right. So exactly, Lauren, right? So to answer your question, right? I answer your question with a question. Why can't I do this? Yeah, sure. Yeah, right. But same eigenvalue is not an issue, right? Like it could be. Remember, not clear because I want V1 and V2 to be different. So I think they're independent, right? That's my assumption. No, not that either. The point is this, okay? The point is, if I do this, I'm bound to fail because this is a structure of the solution corresponding to two distinct eigenvectors. This is a structure of the solution corresponding to two distinct eigenvectors. In other words, if I plug this into this and solve, I will discover that V1 and V2 must be eigenvectors. And so maybe then what Daniel say is correct, that so that's my point. It's not a random decision. When you, I mean, with the T, it's not a random decision. Okay, I mean, it's inspired. But once, so also not random either, right? But when you do that and you carry out this analysis, what you will conclude is that V1 and V2 must be eigenvectors. Okay, if you carry out this analysis, you will conclude that V1 and V2 must be eigenvectors. You want to see that? It's very easy, right? Let's do that. Suppose that I assume that is C1 V1 e to lambda t, right? Plus C2 V2 e to lambda t. In fact, right, this is exactly what's behind our structure all the time. What's y prime? Y prime is C1 lambda V1 e to lambda t plus C2 lambda V2 e to lambda t, right? What's AY? AY is C1 A V1 e to lambda t plus C2 A V2 e to lambda t. Okay, and they must be equal, right? Because that's supposed to be the solution. Now I know, right, there's a confusion where they're both e to lambda t. But let's say, right, I mean, I guess intuitively you mesh like this. Then AV1 equals to lambda V1. That means V1 must be an eigenvector. AV2 must be lambda V2. That means V2 must be an eigenvector too. But do you have two eigenvectors, two independent eigenvectors in this problem? The answer is no, you don't. That's why this structure failed. That's why this structure failed. It's not that you cannot try it. It's not like it's random or it doesn't make sense. It does not solve this problem exactly because we do not have two V1, V2. If you do, right? If we do, in which case, yes, right, there are cases when we do, then this is the structure, all right? That's the confusing part that you must master. If there are two distinct V1, V2, you're fine. But exactly, right, Lauren, that here we do not have two distinct V1, V2. Therefore, the structure that we must try is with the extra t on the right-hand side to get out of, you know, the two eigenvector structure. Because as we plug in, we figure that exactly we only need one eigenvector. The second one is the pseudo eigenvector. So that exactly is what we need in this case. Yeah, okay, that's the important thing. And I will point it out again, all right, as both cases can happen. Any other question? All right, so there is a T here. Yeah, sure, of course. All right. So maybe, but let me clarify my silly mistake. What other choices of V1 can we have here? Okay, for the pseudo eigenvector. So in other words, right, let me ask a question like this, right? If V is an eigenvector, then C times V is an eigenvector. Right, where C is non-zero. That's correct, right? That's obvious. So that's not a question. The question is, if V is a pseudo eigenvector, is CV a pseudo eigenvector? No, because I guess I hide the thing for you. Here, this is exactly what a pseudo eigenvector is supposed to do. The answer is no, because exactly a pseudo eigenvector solves a non-homogeneous problem. Okay, the right-hand side is not zero. So if you multiply by C here, you will change the right-hand side by C. So that's no longer the same. Okay, so if V1 is 0, 1, right, then say 0, 2 is not a solution, right? That's not another choice for V1. But what are choices of? Yeah, but that would not be the V2 that we're talking about. You know what I mean? That would not be the same V2 for this solution. That would not be the same V2 for this solution. Because right, the point is that you must fix the V2 and solve for the V1. Okay, whatever V2 you choose this, fine. But once you choose that, it must be fixed in the second calculation. Okay. But in this system, okay, what are the generic V1? The generic V1, right, would be 0, 1 plus any constant times the homogeneous solution. So I think someone mentioned, right, x1 or something like that. They're expressing this idea, right? So where does this come from, right? This is exactly the idea that you use a particular solution. Remember that particular solution, this is yp plus yh plus cyh. This is your yh right here. This is your homogeneous solution, right? And so the generic structure of a pseudo eigenvector is like that. So do remember that the pseudo eigenvector solves a non-homogeneous problem, okay? So no. But in general, right, the pseudo eigenvector has a structure that is a particular solution, right? Okay, a particular pseudo eigenvector, which this is all you need anyway. So what your friend may come up with is another choice that is going to be a constant times the eigenvector that you obtained from before. So in other words, right, another friend may come up with the choice that is 3 and 1, okay, as a solution for a pseudo eigenvector, which is different from your solution by exactly a multiple of the original eigenvector, because the original eigenvector is the solution to the homogeneous equation. Okay. Any question? All right. So let's look at another example. The example now is going to be 3.5 problem 2. So there they got y prime is 2, 1 minus 1, 4 y. Okay. This is not decoupled, right? This is not decoupled. This is not partially decoupled. So what is determinant of A minus lambda I? It will be 2 minus lambda, 4 minus lambda plus 1. So that's lambda square minus 4 lambda. So that's minus 6 lambda, right? Plus 9 is equal to 0. So lambda equals to 3, right? Are the are the repeated eigenvalue. Okay. Now, if you subtract 3, right, what do you get? So A minus lambda I, right, is equal to minus 1, 1, minus 1, 1, right? So how many eigenvectors do we have? We have one eigenvector here, right, which is 1, 1. Okay. And I guess I'm consciously call this V2, right, because, you know, this is an eigenvector, and we will have a pseudo eigenvector coming up. Okay. Now, how do I find V1? V1 will solve this system. Okay. And you just have to find a particular solution. So what would be a choice of V1 that works? Yeah, or I think 0, 1 also works, right? I think. Right. So your total solution will be C1, right? V1, which is 0, 1, e to the 3t plus C2, V2, which is 1, 1, t e to 3t. Any question? No, because exactly by definition, pseudo eigenvectors solve this system. So if you don't know the right-hand side, how can you solve for it first? I mean, I don't care what you call this, right? You can call this V1, you can call this V2. But then just do remember that the eigenvector is connected with the t term, and the pseudo eigenvector is connected with the non-t term. Yeah, good question, Albor. We'll exactly, actually, I'm going there right now. Yeah. So Will, is that okay? All right. So yeah, question for you, right? Is there, let's do 2 by 2 for now. 2 by 2 matrix with repeated eigenvalues, but full set of eigenvectors. That's actually Albor's question, okay? But to discuss that, we want to ask, is there such a system to begin with? If so, what is it? Give me an example. Such as? No, Daniel, don't ever go there. I don't know what you mean by degenerate, but 0 is not an eigenvector. Don't ever think about it. That would be wrong to begin with. So what do you mean? Yeah, of course. That's what I'm asking. But what example can you give me? 2 by 2. right? I mean, we guess it exists, but without some evidence, right? No one will be convinced. Anyone? Absolutely. The identity is a perfect example here. That's why I have in mind, actually. Yes. Right? What are the eigenvalues? What are the eigenvectors? And suppose you look at y prime equals to ay, right? I guess this is what Daniel means by degenerate. Is not degenerate. I mean, okay, degenerate in math means equal to 0, but I guess he says it's too simple, right? And of course it's too simple, right? No one would even consider this as a system. But suppose you view this from the point of view of eigenvalue, eigenvector solution. What is the solution here? C1, 1, 0, e to a t, plus C2, 0, 1, e to a t, right? Oh, no, that's fine. No, don't be sorry. I'm just saying that me and you don't understand the same thing. So when you say degenerate, I may misunderstand you, but yeah, no, you're fine. Yeah. So, right, but T here would be completely wrong. Yes, you can see that because obviously this has solution e to a t and e to a t, right? So putting a t or t here is completely wrong. And of course, right, it's wrong because, so that's wrong from the decoupled point of view. But from the eigenvalue, eigenvector point of view, it's wrong because it has two eigenvectors. Okay. And that's exactly, okay, compare and contrast this with, right? That's exactly this case I'm talking about. No t, right? No t means you must have two eigenvectors. If you only have one eigenvectors, then the t there helps you to wiggle your way out of, right? One of them being eigenvector. Is that okay? Now this is a trivial example so that everyone can see. We're going to do a 3x3 case. Yeah. I mean, exactly, Will. I mean, like, yeah, sure. But I mean, I choose this because, how to say this, right? Yeah, you're right. Because, basically, right, the solution will be just e to a t anyway, right? So however you want to spin it is e to a t. Yeah, a constant e to a t. Yeah. Any question on this? All right. So this is okay, right? But a little bit too simple, right? So, or degenerate, like Daniel would say. So let's look at 3x3, for example. 3x3 examples. And the idea there will be more clear. So first one, right? So we will look at y prime, right, equals to ay. The first, let's look at a to be 1, 0, 0. Let's do this. Yes, fine, right? Hold on, let's say this. 2, 0, 0, 2, 1, 0, 1, 0, 1. Okay. We looked at this before, right? When we look at just eigenvalues, eigenvector in general. So let's first look at the eigenvalues, eigenvectors of this matrix, right? Lambda, right, is 2, 1, 1 because it's a lower diagonal, lower triangular matrix, right? When lambda equals to 2, right, then you got 0, 0, 0, 2 minus 1, 0, 1, 0, minus 1. So your V1 will be 1, 2, 1, right? When lambda equals to 1, then you got 1, 0, 0, 2, 0, 0, 1, 0, 0. So how many eigenvectors do you have here? For lambda equals to 1, how many eigenvectors do you have? Correct, right? You have 2 eigenvectors. Let's say 0, 1, 0, and 0, 0, 1. Is that okay? So this is a full set of eigenvectors case. So we don't need t here, right? There's no need for t. There's no t here. Your solution will be C1, 1, 2, 1, e to the 2t, C2, 0, 1, 0, e to a t, C3, 0, 0, 1, e to a t. Is that okay? No, it won't work. Because there, then you dabble into the pseudo eigenvector, which will not have anything here. Okay, so in fact, right? Let's demonstrate, right? Your question is interesting, Nam, right? In this way, right? Suppose, right? So Nam's question is like this: suppose somehow you only find V2, which, right, is exactly you know. A lot of students do that, right? You miss the third one. Then suppose you get inspired, right? And you think, okay, it must be pseudo eigenvector. So what do? You construct, right? So V2, right, is 0, 1, 0, right? Then what do you need? You will try to solve, right, A minus lambda I, right, which is this. 1, 0, 0, 2, 0, 0, 1, 0, 0 times V3 equals to 0, 1, 0. What's your V3? What's your V3? Yeah, no solution. Is that bad? Yeah, it's bad. But is that inconsistent? No, it's not inconsistent because, right, there's not supposed to be any pseudo eigenvector here to begin with, right? You're supposed to have 2 genuine eigenvectors. Remember I said, right, it's quite miraculous that, remember exactly this is my remark, that this system is always consistent, right? You see, it's quite interesting. It's not always the case, right? Exactly like the question that Nam raised. If somehow you're mistaken, right, and in the case where you're not supposed to have pseudo eigenvector, and you plug that in and you look for it anyway, you won't find it. It's not there. You cannot find it. Okay. Yeah, Ron, a good question, right? So basically, is the eigenvector correspond to the same eigenvalue? So when we talk about eigenvector and pseudo eigenvector, that's supposed to correspond to the same eigenvalue. Okay, as you see. So I'll do another example. Okay, so basically, for example, suppose lambda, okay, has, let's say, multiplicity 3, okay, and only one eigenvectors. Then the two pseudo eigenvectors will be this. So let's say V1, okay, V3. Then the V2 will solve A minus lambda I, same lambda, V2 to be V3. And then the next one will be A minus lambda I, V1 equals to V2. Okay. It's the same, corresponding to same eigenvalue. So in other words, this guy right here has nothing to do with the repeated eigenvalue down there. It's a different business. V2. So it's like the square equal to V. If you want, it's a square equal to V3. We'll look at it. Okay, we'll look at it. All right. We'll do more concrete examples to address this case. But for now, all right, for now, let me just to recap, right? This example right here is an example with repeated eigenvalue with 3 eigenvectors, with 4 set of eigenvectors. So the solution is just the usual one. Okay, so far? We'll do more examples, okay, with variation on this. So example 2, okay, y prime equals to ay. Now a will be 2, 0, 0. Hold on, give me one moment. 2, 1, 0, 1, 1, 1. Okay, this is a second example. So the difference, right, is here I changed the 0 to a 1. Okay, same system, right, but I changed it to a 1. And it'll make the whole big difference. So first, right, what are the eigenvalues? The eigenvalues is still 2, 1, 1, right? When lambda equals to 2, what do I get? I get 0, 0, 0, 2 minus 1, 0, 1, 0, minus 1. Sorry, 1, 1, minus 1. Okay, so what's my V1? 1, 2, interesting, 1, 2, 3. Fun, 1, 2, 3. Is that okay? Now, when lambda equals to 1, what is it? It'll be 1, 0, 0, 2, 0, 0, 1, 1, 1, 0. Yep. How many eigenvectors do I have here? Correct. So let me call it V3, okay? V3 is 0, right? And then 0, 1. Yes? So this is the example that partially answered Nam and Ron question, right? It's clear that here I need to have a pseudo eigenvector. And I'm in the T case because I only have, this is not full set, right? This is non-full set. Is that okay? So I need to look for a V2, right? I need to look for a V2 of 1, 0, 0, 2, 0, 0, 1, 1, 0 times V2 is equal to 0, 0, 1. All right, I hope that I'm not doing anything wrong here. What, is there any solution here? What is V2? Is there a solution? Or is there no solution? If there's no solution, I'm in trouble. Is there any V2 here? Correct. And exactly, all right. So correct. So first, right, Ron, I think this is partially your question, right? I use this to find V2. I do not use this to find V2. And I think, right, it's clear to you that if I use this to find V2, I will not have V2, right? So that's what I mean by corresponding to the same eigenvalue. And Nam, right, you also see, right, in this case, I have a solution. In contrast to the previous case where it's a mistake, so I don't have a solution. Okay. Any question here? So what is my final solution? My YT is what? My YT will be, what was it, right? 1, 2, 3, e to 2t, right? And then 0, 1, 0, e to the t, 0, 0, 1, t e to a t. Where did I get this structure from? This is exactly the same structure as I discussed in a 2x2. There's no difference here, right? Same idea applies. Any question? Correct. And you asked why? The answer is exactly from this calculation. Yeah, Nam, we'll do that example right now. Yeah, exactly. We'll do that. But first, right, Nigel's question right here. So if you do this, right, blah, blah, blah. I got frozen. Sorry, somehow my iPad's frozen. So where was it? Right, for Nigel's question, right? I start out with this structure, right? And I plug in and I figure out that V2 must be the eigenvector. So right there, right? So V2, the eigenvector, is the one that got the T. V1, right, is the pseudo eigenvector. And so the V1 is the one that does not have the T. So that is exactly what I say when I say, you must put things in the right position, right? So if you swap them, you get the wrong solution. Yeah. Is it okay here? So the difference between this example and this example, can you see it? All right. So now exactly, right? Going to the extreme, right? Where the 3x3 is more fun than 2x2. Nam's question, right? What's the last example? The last example is I will take A to B like this, right? But I change this to a 1. Okay, I'll change this to a 1. So I hope that works. Let's see. So I think that may not work. Hold on. Let's see. 1 0 0. Okay. 2 1 0 1 1 1. I think it might work. Okay. This. So now the eigenvalues have a multiplicity 3. Okay. Let's see how many eigenvectors we have. So when lambda equals to 1, right, we got 0 0 0, 2 0 0, right? 1 1 0. Oh, okay. So maybe let me do this first. All right. Let me do this first. I want this, and then I'll do the other one later. Oh no, it's fine. It's fine. No, this is what I want. Sorry. Huh, apologize. Okay. So first of all, how many eigenvectors do we have here? Yep, exactly, right? This is exactly Nam's question. We only have one eigenvector. Okay. So actually, this also is connected to Ron's question, right? What do we do here? So we revisit that, right? Now we need to, you can guess, but I want to make it more rigorous. So we'll revisit the abstract structure. This time, right, like what Nam said, we will do C1, V1, e to lambda t, C2, V2, t e to lambda t, C3, t squared over 2, e to lambda t, and plug in to discover the roles of V1, V2, V3. Okay. And I think, right, you see why we go to this structure. The reason is we only have one eigenvector. If we have two eigenvectors, then this structure works, right? You only need one t. But here we only have one eigenvector, so you need to go to this level. And so as you see, right, if my memory serves, exactly this kind of thing will be what we discover, right? The two pseudo eigenvectors will be like this. Okay. But I think we're running out of time, so we'll save it for our discussion on Thursday. Yeah, thank you. All right, if there's no question, we'll see you next on Thursday. If there's question, go ahead and ask. Yeah, you too. Thank you. You too. It's on the syllabus. Take a look. I think sometime in the next 2 weeks or so. But take a look at syllabus. Yeah. Okay, you too.